So today we're going to continue on with our atomic physics unit by talking about spectral lines. Now, spectral lines are something we would have covered in previous science courses, but it might be something that seems pretty new to a lot of us. Anyway, here we go. So we're going to continue the discussion about the Rutherford and Bohr models of the atom from last class. So we're literally going to start right where we left off. I think we were on, let me just see real quick, we were on page, if you're following the notes, we were on page 19, just to help you out on that one. So the things we're going to cover today are energy level transitions for electrons. So talking about what happens when electrons move from one energy level to another within a Bohr model of the atom. We're going to talk about spectral lines, both emission and absorption. We're going to talk about the spectra of hydrogen, and we're also going to talk about electron transition series. It's going to be a pretty complicated day today. If you are stuck on anything that we discussed, please reach out to me, send me an email, send me a reminder. You guys know the drill. Anyway, let's get going. So first things first. On page 19, it says, draw a rough diagram to illustrate the movement of electrons between orbitals and the resulting emission or absorption of light. I'm not going to draw it on here. I just literally took my drawing from my answer key that I've got posted. Basically, remember, if you have electrons drop orbitals, so if they go from a higher orbital, like up here, to a lower orbital, what happens is light is emitted. In other words, a photon gets released. And the energy of that photon is equal to the difference in the energy between these levels. Now, on the other hand, if you were going to go from a lower orbital to a higher orbital, in order to get your electron out there, you need to absorb some energy. And that energy, of course, generally speaking, comes from light. So a certain amount of light energy would have to be absorbed in order to get that electron to move to an outer orbital shell. Okay, so in other words, the energy has to get somewhere or come from somewhere in this. Now, theoretically, and we are going to build to that today, theoretically, you could have an electron down in, let's say, the first orbital, and then get all the way up and be released from the electron altogether. So, or from the atom, sorry, altogether. So in other words, this electron could theoretically gain enough energy from an incoming light wave to be emitted altogether. That is something we're going to focus in on today, and we will get to when we get to it. But the more you know, there you go. Now, spectral lines. Bohr's model of the atom helped explain spectral lines that came from glowing solids and gases, both in excited, or in other words, heated states, and unexcited, or in other words, cool states. Now, there's three types of spectra. There's the most simple one, which is just continuous. That's if you had just normal white light, and you put it through a prism, and then it breaks into a continuous spectrum of color. But then there's something called an emission spectrum, which is the one where a bunch of light lines appear within a whole dark spectrum, basically. And this actually occurs from a hot gas that's emitting some light, eventually having that light be transferred through a prism, and then this is what shows up in the spectrum that shows, because it turns out that the light from here is only actually going to have certain lines within a whole spectrum. Last but not least is an absorption spectrum. That's where if light that otherwise would have been a continuous spectrum passes through a cold gas, then those certain wavelengths will get absorbed in the absorption spectrum as well. So they'll show up as dark lines in an otherwise continuous spectrum. Anyway, we'll break down each one of these. Here we go. So first things first, continuous. We're not going to spend a long time on this. Continuous spectra are produced when light from a hot, solid, or high-pressure gas passes through a scattering medium, such as a prism or a diffraction grating. In a continuous spectrum, there is light of all colors with no gaps or breaks in the spectrum. This is brought on because light of differing wavelengths refracts or diffracts at different angles. Okay, so in other words, as we would have remembered from our EMR unit, white light is actually all light all together, all the wavelengths all added together, because different wavelengths will diffract at different angles. That's why it separates into all the colors of a continuous spectrum. Moving on, so emission spectrum. Emission spectra are produced when the light from a low pressure gas, usually heated to an excited state, passes through a scattering medium like a prism. An excited gas is one in which the majority of the atoms are in excited state. The electrons are in higher orbitals. As the electrons fall to lower orbitals, they emit light in specific energy levels and therefore in specific colors. Every atom, and therefore every element, produces a bright line spectrum because they have the unique electron orbitals, each of which emit different energies of photons depending on which orbitals they are falling from. In other words, in plain English, because you can take the high pressure gas, or sorry, low pressure gas that's been heated, because you can take the emission spectra from each of those and get kind of a blueprint telling you what that gas would have been, that tells us that the amount of energy it takes to go from orbital to orbital within the orbital shells must be different depending on the element itself. So every element will have its own different blueprint, its own different orbital map, you could say, saying how those orbitals are going to behave. Now, for some of the emission spectrum, for different things, this is a very blurry image, and I apologize, it's just the best one I could find real quick. Different elements will have different emission spectra, is what I'm trying to say here. So for hydrogen, it would look like this. For sodium, it would look like this. So notice the bright lines appear at different places. Helium, neon, mercury, you get the idea. Moving on. So absorption spectra are produced when white light is passed through a low pressure gas, so a cool gas, before it passes through the scattering medium, right? So in other words, this is where it's coming from an initial source, but then that light has to pass through the cool gas, and those specific wavelengths are being absorbed. So the white light produces a continuous spectrum. However, the atoms in the cool gas absorb energy from that white light. The electrons may only jump into specific energy levels, meaning they only absorb light of specific energies. And as we remember from before, energies correspond with frequencies, and frequencies correspond with wavelengths. It all interconnects. So the specific energies of the light, which cause an electron to jump from an outer orbital, are absorbed by the gas and therefore removed from the continuous spectrum. That's why those dark lines are going to appear, because those specific wavelengths were absorbed by that gas to get the electrons going to a more inner orbital. Now, the dark lines are known as Fraunhofer lines. You don't need to know that. And as before, they are unique to each element. So just like with an emission spectra, an absorption spectra can still be used as a blueprint to figure out basically what kind of element you're looking at. So here's just an example of hydrogen. The top picture is just okay. It's just kind of showing, okay, it's an emission, and then it goes through the actual gas itself, so it's an absorption, and then detection. Now, in this detection chamber, you'd have your prism, which then breaks it off, right? So basically what would happen with hydrogen is those dark lines would show up at those certain wavelengths, which of course correspond to certain frequencies, which of course correspond to certain energies, right? So the energies at those specific locations are being absorbed. That's why those dark lines appear. Okay, so summarize the three types of spectra on the following chart. For continuous spectra, how is it produced? Well, just light from a hot solid or high pressure gas. There's no electron movement because it's a continuous spectrum. Now with emission, which is bright line, so bright line in a dark field, emission is light from a low pressure gas in an excited, or in other words, a heated state. So what's happening is they are emitting electrons. So they're going out toward or down towards the nucleus, okay? For an absorption, light is passed through a low pressure gas. So there's an absorption of energy, so light is moving out away from the nucleus to the higher energy levels, okay? Hopefully, I think I might have had that backwards in a previous slide, but this one is good, believe me. Absorption, of course, you're absorbing energy. So in other words, you're gonna move to an outer energy level. For emission, you are emitting energy. So energy is being released in terms of like a photon, basically. Hence why they show up as those bright lines. Those are the photons that are being released. So the electron itself is moving down towards the nucleus. Make sure that one's pretty straight. So you'll definitely want this chart if you haven't copied it down already. All right, so for the hydrogen atom, I'm going to zip through this real quick because some of this early stuff is just too much. Basically, elements higher in the periodic table have numerous combinations of orbital level jumps and falls, and therefore have very complex spectra, both within and outside the visual portion of the spectrum. So that's kind of interesting. Those spectral lines theoretically could show up in ultraviolet, or they could show up in infrared, right? Don't worry about that. The first element that scientists discovered spectra and were able to describe it was hydrogen, which only has 4 lines in its spectrum within a range of visible light, so 400 nanometers to 700 nanometers. Johann Balmer was able to deduce a formula which described the 4 visible lines. He came up with this. You don't need to know that. I'm moving on. Balmer's formula was discovered by trial and error, and it was not known why the formula worked. Later, other lines outside the visible spectrum were observed that followed the formula. However, other lines that the formula could not account for were also discovered. The new lines were ones in which the electrons weren't jumping from the lowest orbital, n=2, but instead were jumping between other orbitals. The formula was rewritten to account for those new lines. There it is. You don't need to know it. Do not worry. Like, no, don't worry about this. Moving on. All right, so the hydrogen atom. In the hydrogen bright line spectrum, a bright line is produced when the atom releases energy. That is, when the electron drops from a higher energy level to a lower energy level. So in other words, if you got your energy levels, right, you have a bright line that's produced when it drops, because when it drops, there's a photon that gets emitted, right? So that's where that photon's going. It's that bright line that's been produced. That's what's actually what that line is. Now, in the hydrogen dark line spectrum, a dark line is produced when the atom absorbs energy. Now, remember, absorbing energy means that that electron's going, oh, I got more energy now, I can go to a more outer shell, right? So that amount of energy is, of course, provided by a photon. That's why the photon disappears. That's why it's a dark line. It disappears because the photon was absorbed by that electron. So going over it one more time, the reason we have an emission spectrum when there's an atom releasing energy, it's being emitted, is because the emission is really these bright lines, okay? And it emits an electron when it loses some of its energy by going to a lower energy level. The other one, absorption, the reason these dark lines appear is because those specific lines are being absorbed by your atom, and therefore they're being absorbed into that electron, moving it up to an outer electron shell. Okay, hopefully that makes things a little bit clearer. That slide hopefully clears things up. Moving on. All right, this is too much information as well. You don't need to know this. There's 5 series names for possible electron transitions within a hydrogen atom: Lyman, Balmer, Paschen, Brackett, and Fund, I think. Fund, I think is just how it is. You don't need to know them, but the only one that's really notable is Balmer, the one that was named after the guy who figured most of this out. It's the only transition that produces visible light, right? So the Balmer series, that second lowest orbital, that's the one that's actually producing those visible light rays that we're seeing within a hydrogen spectrum like this one right here. So Balmer series are responsible for these. You don't need to know much about that. Moving on. So Bohr's atomic model also helps explain the repetition of chemical properties in the periodic table. Bohr suggested the properties of an element depended on the number of electrons in the outmost orbital. These outer electrons are known as valence electrons. For those of you who've taken chemistry, that should be a familiar term to you. The electrons that are in that outermost orbital are your valence electrons. Now, the energy levels between orbitals are not equally spaced. The first orbital, n is 1, is the lowest orbital. When an electron is in this lowest energy level, the atom is said to be in a ground state. The amount of energy required for the energy to move between orbitals is simply the difference between the orbital energy levels. Okay, that shouldn't be too big of a surprise, right? So there's orbital levels, or energy levels for each of those orbitals, and the amount of energy it takes to go from one to another, or vice versa, is just the difference between them. Now, ionization, where you actually get something ionized, where it becomes an ion, and remember, it becomes an ion if it gains or loses an electron, occurs when the electron is given enough energy to escape the atom. Now, for all intents and purposes, we say that the escaping of an atom is where n is equal to infinity. Remember, n is 1 is your lowest orbital, then you have n is 2, n is 3, n is 4, and onwards. But we say n is infinity just by standard. To say that it's gone now. It's left the atom. There's no more orbital level. It's out of there, right? All right, so draw the orbitals for hydrogen with their corresponding energies. As you can tell, I literally just copied this right out of my answer key. What I want you to note is going from your lowest orbital to your second lowest orbital takes the biggest difference of energy. Like that's almost a difference of 10 electron volts, right? But then going from your next one to your next one, it's not as big of a difference. Now, I didn't draw this to scale by any means, but hopefully you get the idea that this is supposed to be spaced out further. This is now a little closer. This is closer still, and so on. So I drew 6 orbitals for hydrogen. N is 1, N is 2, N is 3, all the way to 6. And these were the energy levels. Again, I just pulled this from a resource. It'd be nice for you to jot it down, but I don't think you'll ever not be given this. I'm pretty sure it'll always be given to you in any questions, certainly on a test or something. I'm not going to have you remember this or anything. So, but there it is, right? So those are the orbital levels. And notice, by the way, the energies are usually listed in electron volts. That's just because it's a nicer number to deal with. You know, if it was in joules, it would be some crazy scientific notation thing. But electron volts are just a little bit more comfortable for us here. Now, you might be wondering, why are all these numbers negative? That's also just something they do by convention. Theoretically, where you have n is infinity, that would correspond to exactly 0 electron volts. So if you were wondering, oh, how much energy do I need to go from my first orbital to ionization? Remember, ionization is where that electron literally just leaves and goes to n is infinity. Well, it's just equal to this piece right here. And that's why they do it by convention. So you can see, oh, okay, that's my energy level, negative 13.6 electron volts. So by all means, that is the lowest energy level. That is the smallest amount of energy. But the reason it's based around 0 is so you can figure out quite easily how much energy it would take to escape the atom altogether. So in other words, if you had an electron in the first orbital level here, it would need 13.6 electron volts to leave that atom altogether. If you wanted to go from this to here, you would need just the difference between these two, whatever that would be. It's like 10 something, right? So anyway, moving on. Now, briefly outline the strengths and weaknesses of Bohr's atomic model. Well, some of the strengths of his atomic model are it explains the existence of spectra. So as we've talked about today, of course, whether it's an emission or an absorption, Bohr's atomic model and the whole concept of different energy levels, different layers, right? You know, like atoms are like onions, ogres are like onions. Anyway, I'm not going to do a Shrek joke right now. Yeah, it explains the existence of spectra. So whether you're absorbing or emitting, those energy levels explain that, right? They explain why you get a bright line or why you get a dark line, okay? It also explains how atoms remain stable, of course. They like going to a stable state. They like existing just in those certain energy levels. In particular, they love being in that ground state, way down here. It also explains ionization, so it explains why a certain amount of energy is required to get you know, an atom ionized. It explains that. And it also connects with Bohrs' formula as well as quantum physics. Don't worry about that too much. Now, some weaknesses is it couldn't explain the Zeeman effect. I'll show you what that is in a second. You don't really need to know that, but it's basically where if you have a static magnetic field, the energy levels start splitting up. Okay, so in other words, your absorption and emission line spectrums also become split up. It gets really weird. Now, it also couldn't explain spectra created by atoms or ions with more than one electron. That was quite a clear weakness of that. Like if you had more than one electron at any given time, you know, it's going to be a challenge to determine how the spectrum behaves with that under his model. Not that it was bad or anything, it just made it a little more difficult. Now, it also couldn't explain the formation of chemical bonding of molecules. That came later, don't worry about that. So with the Zeeman effect, again, that's just where spectral lines can split into several components if a magnetic field is present. This is an awful picture. I don't remember where I got this from, but basically under a normal circumstance, you get like a bright line right here. I don't know why they didn't put it in color, like that's the most annoying thing. But you get a bright line here, but then if you brought in a magnetic field, it'll split that line up, okay? Bohr's model doesn't explain why that happens. We don't even need to know why that happens. Let's move on. All right, last question here. This actually went way faster than I thought. We're like 17 minutes into this. So if an electron is in the negative 1.6 eV energy level, determine the minimum frequency of a photon that would ionize the atom. So this comes into what I was talking about just a minute ago. Remember, this one's for mercury. It's not for hydrogen, so that's why we got some different numbers here. But if you're here in the negative 1.6 eV energy level, in order to become ionized, you have to get to n is equal to infinity. Now, what's kind of interesting here is they actually drew it. See this line that says 0 eV? That's technically your n is equal to infinity line. It's your infinite, quote unquote, energy level, because that isn't really an energy level. That's just a point at which where the electron has escaped and it's now free. That's what it means to ionize. So really, in order to do this, we need to gain, the math here is easy, we need to gain 1.6 electron volts. Now, where does that energy come from? Well, of course, it comes from a photon that's going to come in and strike here, and then that's going to absorb that energy and then send it out to ionize it. So again, we need to absorb 1.6 eV of energy. That's how much energy we need to absorb. The energy is being provided by a photon, so we need to use a formula that represents the energy of a photon. Now, here's the good news. Since we're looking for the frequency, we need to remember that E for a photon, this is from the end of our EMR unit, E is equal to H times F. We want to find that frequency. Well, here's how it's going to work. We have our E. Our E is actually listed in electron volts, so it's 1.6 electron volts is equal to H. Now remember, H has two different possible units. There's one in joules and there's one in electron volts. Now's the time to use the electron volt one because we have electron volts. So it's 4.14 times 10 to the negative 15, and then times that by the frequency. Divide away this 4.14 times 10 to the negative 15, and you're going to find your frequency is going to equal to 2 sig digs, 3.9 times 10 to the 14 hertz. So in other words, that is the frequency of a photon that will ionize a mercury atom that's got an electron in that energy level. See, not really too big of a deal. It's just a matter of looking at your energy level chart that you're given and finding the appropriate energy level differences. And again, we could assume this is n is 1, and this is n is 2, this is n is 3, this is n is 4, and whoop, n is 4. And yeah, you might say, oh, that's n is 5. Really though, when it's 0 EVs, we just say by convention n is infinity. That's it. That's all we're going to worry about today. Holy smokes. Anyway, so for practice, Rutherford and Bohr worksheet, that's page 24 to 26. Super important that you get this one done. There's a few questions in there that are like, oh, describe this, this, this. Don't worry about that. I want you to do some of the more later ones. So especially page 25 and 26, really, if you wanted to say 25 and 26, there you go. I just cut it down for you a bit. Those ones at very least are the really important ones to be doing. As usual, make sure you're contacting me if you have any questions, and best of luck, guys.